Okay, thanks. Well, I'm going to talk about on quantum obfuscation. This is very new work. I'm Bill Fefferman, a postdoc at Quicks here in Maryland. So it's a great privilege to be able to speak here, so close to home. And this is joint work with my collaborator Gorian Alagich at the University of Copenhagen. Okay, so I'm going to give a quick overview of my talk. I'll have three parts. I'm going to say, first of all, some definitions. So what is obfuscation in both the classical setting and in the quantum setting? Then I'm going to talk about applications. So, why would you want a quantum obfuscator or a classical obfuscator? Okay, a lot of these applications will seem way too good to be true, and so I'll ask, how feasible should they be? We'll kind of go back down to earth and we'll ask, should these notions be possible or not? Okay, even in a quantum world. Okay, so some definitions. So let's talk about the classical case. So a classical black box obfuscator is an algorithm O that takes as input some form of computation. In this talk, I'm going to assume it's a circuit, C. Okay, it's going to output a circuit O of C with three properties. Okay, so first, the functionality of O of C should be the same as the functionality of C. So this is easy to demand classically. You just say that the same inputs x may map to the same outputs. Okay, so for all inputs x, C of x should equal to O of C of x. Okay, the efficiency should be preserved. This is also not hard to be intuitive about. Classically, it should just mean that the size of this obfuscated circuit, O of C, should be, no bigger than some polynomial in n, the input length. Okay? And then finally, we'll have the all-important black box obfuscation property, which roughly speaking says that anything that can be learned about the obfuscation, O of C, could have just as well have been learned from black box access to C. Okay, so black box access here just means I get to run C on a number of inputs, and from the input-output relations that I learn, discover something about the obfuscation. Okay? So formally speaking, what this means is for any efficient adversary algorithm A that gets to use that gets to see the obfuscation of the circuit, there exists some simulator algorithm S that gets to use the circuit as a black box that kind of learns just as well whatever A learned. Okay. So now our focus today is going to be on what should this mean quantumly. Okay. And so at the very least, every algorithm I talked about in the prior discussion, and there were a lot of them, should be quantum, right? So that's the input circuit itself, the adversary, okay, which sees the obfuscation, the simulator, which gets to run the circuit as a black box, and the obfuscation procedure itself should all be quantum algorithms. Okay, so at the very least, I think this is what it should mean. Additionally, we're going to generalize the output of the obfuscation, O of C, so that it will be, in general, a polynomial in n qubit quantum state, okay, that gains functionality through an interpreter algorithm, J, okay, which is some efficient algorithm that comes with the obfuscation algorithm, O, okay, and, kind of is able to, it uses this obfuscated state to run the circuit C on any input state, sigma, okay? Okay, good. So now, this is some abstract definition, which kind of, it might not be clear why it's so useful. So let me give you some informal sketches of applications, and I stress that there are some caveats that come with these applications that, of course, I'm not going to mention. But I think the idea should be pretty clear. So first of all, one amazing thing you could do if you had a black box obfuscator is you could, in principle, transform a private key encryption scheme into a public key encryption scheme. Okay, so we're used to thinking of these tasks as very different. Okay, in general, for example, we used to think, private key crypto schemes or symmetric encryption schemes, we have a pretty good handle on them, right? Whereas public key schemes, we usually have to make some kind of hardness assumption, like RSA, we have to assume that factoring is hard, right? So it would be really great if we had alternative constructions of public key crypto schemes, and I'm saying that a black box obfuscator would kind of allow us to kind of make an equivalence between the task of making a private key scheme and a public key scheme. And the idea is extremely simple. We just publish the obfuscation of the private key encryption algorithm, ENC-K. So this would normally be a really bad idea. We would not want to do this in general, right? Because we'd be afraid that the algorithm might leak what the secret key is. Okay, but this is precisely what this black box guarantee is telling us is telling us that we can't do. Okay, if I look at the source code of this obfuscated encryption, I can't discover what this key K is. Okay, so now everyone can encrypt by running their plain text, on this obfuscated encryption algorithm, but only the secret key holder can decrypt. And again, this is because of this black box property. Right, fully homomorphic encryption. So here we go again. This is somewhat of a holy grail topic in cryptography, and I'm here telling you that with a black box obfuscator, this would be a completely trivial problem. Okay. So here's what we would do. Of course, we just suppose we want to perform some computation on the encryptions of 2 bits. We'd take some public key encryption scheme, we'd use the secret key to construct an algorithm that performs the computation in the naive way, right, by decrypting, applying the operation, and then re-encrypting. Okay? Now we'd publish the obfuscation of this algorithm along with the public key. Okay? So it sounds like an absolutely amazing thing. Right, so, and now I'll also say some purely quantum applications. So one thing when we talk about one thing we talk about is public key quantum money, which would require a quantum obfuscator. I'll just tell you what the goal is, and I won't sketch how this works as an application. But the goal is very simple. The idea is we want a mint that produces bills in the form of quantum states. Everyone can verify authenticity of a bill to make sure that the mint actually produced this state. But somehow, using the no-cloning theorem, we should obtain that no one can make forgeries, can copy. Okay? So I think this is a very natural thing to desire in a quantum world. A lot of people talk about this. But now it's time to return to Earth, okay? So the question is, how feasible is this notion of obfuscation, even in a quantum world, okay? So in the classical world, a paper by Barak and others crashed this party a long time ago, okay? So in particular, they show that there exist circuits that cannot be black box obfuscated. Okay, and in particular, they construct a circuit from which an adversary that's given access to the obfuscation of C gains more information than a simulator could that has black box access to C. Okay, so let me describe this proof to you. It's very nice. It's very simple. So here's what we do. We're going to choose 2 n-bit strings uniformly at random. I'm going to call them A and B. And now we're going to consider 2 pairs of circuits, so 4 circuits in all. The first pair is going to be as follows. It's going to be what I call CAB, okay? It's going to be always 0, okay? Always the n-bit 0 output, except for one silly input, okay? In the case that the input x is equal to A, C of A will output B, okay? And then the second circuit in the first pair will be a circuit I'll call DAB, okay? Which I want to think of as taking a classical description of a circuit, okay, C, and outputting 1 if C maps A to B, okay, and otherwise it's going to be 0, okay? So this is the first pair. The second pair is going to be extremely similar, okay? The first circuit is going to be called Z, and that's going to be always 0, independent of the input. It's just all 0, right? And the second circuit will be exactly the same as the second circuit of the first pair, okay? It's just going to be this DAB circuit. Okay? All right, and here's the key point. So why did we just define these circuits? Okay, the key point is the following. Suppose someone handed to you either the obfuscation of the first pair of circuits, okay, the obfuscation of C and the obfuscation of D, okay, or the obfuscation of the second pair of circuits, the obfuscation of Z and the obfuscation of D, okay? I claim that there's an easy way to tell these apart, even if I don't know A and B. Okay, and the answer is obvious, and it's to run them on each other, right? Because notice that when I run D on C in the first case, I'm going to get 1, right? Because C maps A to B, okay? But in case 2, when I run the first circuit Z on D, okay, I'm going to get 0, Why? Because Z does not map A to B. Okay, it always maps to 0. Okay? But notice that any simulator that just has black box access to either pair, okay, and is ignorant of A and B can't do this. Okay? To the simulator who just gets to query these circuits, they look identical. Okay? Because, you know, they are very, very close. They're only different on one input. Okay? So that's the idea. But so how do we make this more formal? And this becomes to get, much more detailed. So first of all, how do we go from pairs of circuits to single circuits? Okay, which is what we want at the end of the day. Well, this is not hard, at least in principle. The idea is to create a combined circuit that uses an additional input bit as like a flag bit. So you know if that bit is 0, it runs the first bit circuit in the pair on the input. If the bit is 1, it runs the second circuit in the pair on the input. Okay, so let's let F be the combination of C and D, okay? And let's let G be the combination of Z and D, okay? So now, an adversary given as input, either the obfuscation of F or the obfuscation of G would like to tell them apart, okay? And it'd like to tell them apart by doing the obvious thing. It's going to make a copy of the obfuscation, and it's going to run the obfuscation on itself. Okay? Well, here's the problem. So this sounds like a great idea, but there's a little problem, which is that it's completely wrong. Okay? And the reason it's completely wrong is because you can't run a circuit on itself. Right? The input register, because it's a circuit, is a fixed length. Okay? And the description of the circuit in general is much larger than that fixed length, because a circuit is more than just its input length. Okay? And so you can't run a circuit on itself. It doesn't make any sense. Okay? The input length is simply not large enough. And so this sounds like this should be some easy technicality to fix, but in fact, fixing this requires most of the technical work in Barak's paper. Okay? So let me sketch to you how that works. And in fact, this will also be the difficulty quantumly. Okay? So our goal is we're going to want to modify this circuit D, okay, so that two properties can hold. So one, the adversary can use this circuit, D, to test if a given circuit, C, maps A to B, okay? And it needs to work even if the description of C is longer than the input length of D. That was the problem in the prior case, okay? And then crucially, this is the second property, it should keep A and B hidden from parties with only black box access to D, okay? Because if we let the simulator discover what A and B are, we're all dead. This is done, right? There is no purpose to doing this. Okay, so here's the solution. We're going to construct a new D, which I'll call D prime AB, that combines three circuits. The first circuit is going to output the encryption of A, okay, in some private key crypto scheme. The second circuit will provide the ability to perform binary gates on encrypted bits. Okay, it's like a homomorphic circuit, right? And then, so we'll decrypt the encryption, apply the gate, and then re-encrypt it. Okay, and the third circuit will test whether a sequence of encryptions consists of the encryptions of the bits of B. Okay, so why does this work? Okay, it's intuitive. I guess intuitively it's pretty obvious, although it turns out to be quite tough to make it work in actuality. But the idea is just if we're given the obfuscation of C, we can test if C of A is equal to B by using these three new circuits, and we're going to use them in the obvious way. We're going to start by asking for the encryptions of A. Right? That's using the first circuit. And then we'll use the second circuit to kind of homomorphically apply each gate of C to the encryption of A, so one gate at a time. Okay, and then of course we'll use the third circuit to check that these are the right encryptions. Okay, that this is an encryptions of B. But what we can prove, and this uses properties of the encryption scheme, okay, is that if we have only black box access to D, okay, we can't learn A and B, which is precisely the goal of this whole thing. Again, if we could do this, if we could learn A and B from black box access to D, everything would be off. And this follows from what we call IND-CCA1 security of this private key encryption scheme. Okay, so technically speaking, to get such an encryption scheme, you need a one-way function. So this shows that one-way functions imply that black box obfuscation is impossible. Separately, we can also prove that efficient black box obfuscation implies one-way functions. So that shows that efficient black box obfuscation is impossible. Okay. Okay, so how do we adapt this to the quantum case? All right, so there's kind of two cases that I want to think about. In the first case, the obfuscation has classical outputs. Okay, so in other words, it's the obfuscation of a the obfuscation will be by itself the classical description of a quantum circuit. Okay, so it's not hard to make unitary versions of Baroque circuits, F and G. Okay, that's not the hard part. But the hard part is that we run into exactly the same problem as before, which is that how does an adversary distinguish the quantum circuit obfuscation of F from the quantum circuit obfuscation of G? Okay, it has this input length problem again because they're circuits, and we have a similar solution. Okay, the idea is to construct a modified quantum circuit that kind of homomorphically runs a given quantum circuit on the encryption of A and checks that the output is the encryption of B. Okay, but of course, quantumly, this is far from trivial. So it needs a construction of this so-called in CCA1 private key encryption on quantum states. Why is it on quantum states? Because when you're homomorphically applying this quantum circuit, at any point in its computation, it's going to be in some quantum state. Okay? And this is what we want to encrypt. Okay, and so I'll just give a brief advertisement. We have another paper on this with other authors, which is also at this QCrypt. I think it's going to be given tomorrow, which is talking precisely about these issues, these computational security of quantum encryption. Okay? Okay, but now the second case is I think, far more interesting, which is what happens if the obfuscator outputs general quantum states. Okay, and in this case, the no cloning theorem is going to prevent us from copying obfuscation states, right? So it's not clear how we can run the state on itself, even if we have all of this encryption and homomorphic oracle and so on. So what we can do is say that in the case that we can reuse the obfuscation at all, so in the case that it can be cloned even a small number of times, we can still achieve impossibility. Okay, but the general case in which the obfuscator just gives only one copy, right? We still don't know how to prove that this is impossible. I'm kind of running out of time, so I'll go through this quickly. I was talking about black box obfuscation, but you can also ask about other notions of obfuscation, where instead of this black box guarantee, we have something like this. So this is called statistical indistinguishability obfuscation. And the demand there is that if I give you two functionally equivalent circuits, C1 and C2, the obfuscations, row 1 and row 2, are negligible in trace distance. Okay, so this is a perfectly reasonable thing to demand. We show that this is impossible, okay, but conditionally. I mean, if this was the case, if we had such a statistical indistinguishability obfuscator, then nasty things would happen in complexity theory. So SCK would be equal to p-space. Okay, maybe I won't get into this in too much detail. The idea is that is very easy though. If there's these kind of two problems, one is called quantum circuit distinguishability, right? And that's basically given two quantum circuits, C0 and C1, are they functionally similar? Okay, this is a p-space complete problem. And then there's quantum state distinguishability, which is roughly speaking, given two efficiently preparable quantum states, row 1 and row 2, are they close in trace distance? Okay, so this is QSZK complete. But if we had a quantum statistical indistinguishability obfuscator, these two tasks would in some sense become one. Okay, you could kind of use this, we show that you can use this obfuscator, this statistical indistinguishability obfuscator, to kind of solve this first problem, this quantum circuit distinguishability problem, with this second, with a box that solves this second problem. And that's what gets this, this complexity result. Okay, so in my last slide, let me tell you that there are just some surviving notions of quantum obfuscation that we don't touch, okay? So one, as I said, is quantum black box obfuscation, very strong notion, okay, but with an absolutely unclonable output, okay? And in that case, maybe the surprising thing is we can get many of our applications to survive, okay? These applications that everyone in the room, I'm sure, agrees seem too good to be true, okay? But in fact, we can't prove that this one case is impossible. Okay? And then there's also computational indistinguishability obfuscation, which roughly speaking means if C1 and C2 are functionally equivalent, then their obfuscations are computationally indistinguishable. And I'll leave you to read this paper of Watros to say exactly what that should mean. And we give an application for this. It's called quantum witness encryption for QMA. I won't describe what this is, but what I will say is that classically the existence of witness encryption for NP would have many useful applications. In fact, some of these applications are strikingly similar to the applications I was talking about in the first place that seemed too good to be true. Okay? Okay. Last thing I'll mention is that classically there are candidate I/O constructions, and it would be interesting to see, what these say quantumly. So if we can make these, a quantum indistinguishability obfuscation construction. Okay. Thanks.